In this data-driven world, we're surrounded by an ocean of information. But amidst the abundance, we can find ourselves lost, navigating the labyrinth of data without a clear direction. It's like chasing after wild geese, searching for meaning in the chaos. But how can we stop this? How do we define purpose from large amounts of data? How do we get objectives to explore? Picture a grand system of how the world works, composed of numerous moving parts. It could be the education system, the realm of religion, the corridors of government, or the vibrant world of business. This system is a complex web of interconnectedness. While we may not fully comprehend the inner workings of every component, we can zoom in on one of these moving parts and strive to understand it better. Our intuitions play a significant role in shaping our understanding of these moving parts. They serve as subconscious integration of our lifetime experiences, conditioning, and knowledge, coupled with our cultural and emotional biases, as articulated by Bruce Henderson, the founder of Boston Consulting Group back in 1977. Intuition often steers our decision making, as it provides a quicker route to assumptions and how a particular component functions, compared to the exhausting fact gathering and analysis. But how do we go about creating clear objectives from these intuitions? In science, these intuitions are referred to as hypotheses. Objectives are born by subjecting our intuitions to scrutiny, verifying their accuracy, and if we're fortunate, extending our objectives to explain why a certain intuition holds or is false. It's crucial to note that we can validate if something is true without necessarily understanding the underlying reasons behind it. We can test the effects of a phenomenon without fully comprehending its inner workings. Solid hypothesis often entails a broad intuition about what occurs when we take certain actions, accompanied by a series of reasons elucidating the underlying mechanisms. The fun part is then using data to challenge or validate our intuitions, asking ourselves if the data aligns with our intuitive understanding of how the system operates. When the data confirms our intuition, we rejoice because we have turned a mere hypothesis into an observable fact. This newfound certainty allows us to make more informed decisions based on our intuitive understanding. But what happens when the data contradicts our current understanding? That's when the journey takes an intriguing turn. It could be a humbling moment of realizing we've been approaching the analysis incorrectly, prompting us to recalibrate our methods. Or it could be a thrilling revelation, an opportunity to uncover new insights that challenge the existing paradigm. In either case, there's always something to be learned. Now let's embark on a wondrous journey into the realm of football, the beloved sport that captures hearts worldwide. To truly understand the ability of a football team, let's use the framework explained earlier, breaking it down into two essential components: their defensive ability, or their capacity to prevent the opposing team from scoring goals, and their offensive prowess, or the ability to score goals themselves. Now let's focus on the defensive side of the game, where the battle is fought to prevent opposing team from scoring goals. As the great American footballer Christy Rampone said, "If we score, we might win. If they never score, we can't lose." Profound, isn't it? This quote beautifully highlights the importance of a strong defense in avoiding defeats. Let's put it to the test and ask ourselves, do good defensive records indeed lead to a lower loss rate in matches? Let's kick things off by delving into the data for the 2022-23 English Premier League football season, focusing on the top 4 teams. To tackle this question head on, we must decipher what truly constitutes a remarkable defensive record. A sensible starting point could be to examine the average goals conceded per game throughout the season. This metric paints a picture of a scenario where all the goals conceded are evenly distributed across the entire campaign, providing us with a glimpse into their ability to keep the opposition at bay. These are the average goals conceded per game by the top 4 teams. Newcastle and Manchester City shine as defensive powerhouses, surpassing Manchester United and Arsenal. However, we can't be too hasty to draw conclusions based solely on this statistic. When we rely on the mean as a measure of centrality, its interpretation can vary depending on the shape of the data. If the data exhibits symmetry, where extreme values don't significantly impact our assessment, the means tend to hover around the midpoint. This midpoint indicates an equal number of observations with lower and higher values, creating a balanced perspective. However, when dealing with non-symmetrical data, the mean deviates from being the midpoint and instead becomes the balance point. In such cases, a team conceding a high number of goals in a single match can heavily influence our perception of their defensive capabilities, regardless of their overall performance throughout the season.
Remember, average goals conceded per game only provides a glimpse.
To truly grasp the heroes of the backline, we must explore deeper. Let's plot the number of goals scored in each match played by these four teams alongside their means. The plot reveals an interesting twist. The average goals conceded per game by Manchester United is significantly influenced by a couple of extraordinary matches. These games sway the overall picture, obscuring the team's true defensive capabilities. There is another statistic that preserves the midpoint. The median preserves this midpoint because it is robust to the extreme values one might have in the data. A statistic is said to be robust if removing some data tends to not change the value of the statistic. Now let's turn our attention to the median for each team. All four teams share the same median of 1. Whilst this may not offer us groundbreaking insight and fails to provide substantial insight into their defensive prowess, it does highlight a common midpoint across the board. Acknowledging the influence of extreme values on our mean and the limited information we got from the median, perhaps it is time to turn to a statistic called the trimmed mean. This statistic discards a proportion of the highest and lowest values, enabling us to focus on the core dataset. Just like in Olympic scoring, where they discard the lowest and the highest scores to weed out the impact of biased judges and extreme ratings, the trimmed mean can help us minimize the effect of those abnormal matches. What if we trimmed 10% of our observations, excluding the 2 lowest scoring and the 2 highest scoring matches? A different perspective emerges. Manchester United's defensive performance aligns closely with Newcastle and Manchester City, challenging our previous notion. Meanwhile, Arsenal's defensive frailties become more prominent when compared to the other 3. We've only just scratched the surface. Can you notice how the number of goals each team has scored is spread apart? Let's casually explore some fascinating statistics that allow us to understand this spread. Let's start with variance. The variance measures how far data points are from the midpoint. Often, we use the mean as a rough approximation of this elusive midpoint, but we know that the mean is not always the most robust measure. The distance between an observation and the midpoint is simply called the deviation. Since distance can't be negative, we have to find a way to transform the negative deviations. And in the case of variance, we take the square of all deviations. By adding up these squared deviations and dividing by the number of observations, we get the variance. Oh, and when we're working with samples instead of the whole shebang, we divide by n-1 to inflate the variance for a more robust statistic. This is called a Bezel's correction. Statisticians have shown that for small sample sizes drawn from a population, the sample variance is smaller than the entire population variance. So they use this n-1 trick to help inflate the variance and account for the lack of representativeness and other issues that come with smaller samples. Another explanation is the degrees of freedom. And this means how many parameters you have to hold constant relative to the number of samples while solving this equation. With variance or standard deviation, the mean is the value we had to hold constant. Therefore, the degrees of freedom is n-1. In modern practice, the difference between n-1 and n is negligible due to larger sample sizes. To make the variance more interpretable, we can look at its sibling, the standard deviation. It's simply the square root of the variance, returning the statistic to the same unit as the variable being measured. A higher standard deviation indicates a greater dispersion of goals conceded. And we can see that the standard deviation quantitatively captured the large spread of goals conceded by Manchester United that we saw on the graph. The standard deviation also offers an interesting property when dealing with symmetric data. In a theoretical normal distribution, approximately 68% of the data falls within 1 standard deviation from the mean, 95% within 2 standard deviations, and 99.7% within 3 standard deviations. So if our data was symmetric, we could use Manchester City as an example and say that 68% of their goals lie between 0 to 2 goals. However, our early observation from the mean suggests that our data may not follow a symmetric pattern, and therefore this nice property of the standard deviation doesn't apply to our data. One downside of the standard deviation is that it loses some of its interpretive value when the data is not symmetric. It also assigns more weight to larger deviations than smaller ones because we square the deviations. This means a few high deviations can heavily influence the standard deviation. The reality is that we didn't need to do all of that to understand the spread of our data. There are other forms of calculating variability that simply just take the absolute value of the deviation and then take the average. This is known as the mean absolute deviation. This metric is more intuitive because it literally tells you what the average deviation between your data points and the mean is. However, as you dive deeper into statistical concepts, especially in optimization related problems, you find out that using the squared transformation of deviations has some nice benefits, but for simply understanding the spread of the data, it is not necessary. Let's not forget that we can understand the spread of the data by actually looking at the percentiles of our data. A common measurement of variability is the difference between the 25th percentile and the 75th percentile, called the interquartile range, or IQR. Imagine if we randomly took some of the goals conceded in 8 matches played by Manchester United, and then sorted them out in ascending order. Since we have 8 data points, to find the location of the 25th percentile, we simply take 25% of 8, and that's the second index. And we take the mean of the second index and the index that follows. For the 75th percentile, we take 75% of 8, and that's the 6th index. And so we take the mean of the values in the 6th and the 7th index, which gives us 4.5. The IQR is simply the difference between these two percentiles, which is 3.5. If you collect repeated samples of a dataset, the IQR range would not change by that much, offering us a robust metric for assessing the spread of our data.
So this is what the summary stats will look like for our data. As we peek into our dataset, we witness the mighty Newcastle with the lowest standard deviation and IQR, demonstrating their consistent defensive fortitude throughout the season.
On the other end of the spectrum, Arsenal emerges as the wild card, exhibiting a larger standard deviation, indicating a wider range of defensive outcomes. But beware, these measures alone do not paint the full picture. Although it's nice that we've calculated the summary statistics, perhaps there's a way to show more details without losing simplicity. This is where graphs tend to do their thing. Graphs are the great storytellers of the quantitative world. They possess the remarkable ability to convey complex insights with, elegance and simplicity as well. Let's recall some of the few things we've been trying to understand about our data. We've tried to infer what the shape of our data is. Is it symmetrical or is it not symmetrical? Are there outliers in our dataset? And we can start by exploring the box plot, a data visualization method crafted by John Tuckey, a top lad. This nifty visualization relies on percentiles to give a snapshot of our data and sniff out any outliers. And here's how you make one. Imagine we have some data generated from a normal distribution with a mean of 5 and a standard deviation of 2. First, Tuckey pinpoints the median, which is the 50th percentile, and draws a rectangular box around it. Boxes' upper and lower sides represent the 75th and 25th percentiles, and they form what we call the IQR, as we've discussed earlier on. Extending beyond the bounds of the box are the upper and lower whiskers. The upper whisker stretches out to explore anything beyond Q3 plus 1.5 times the IQR, whilst the lower whisker embarks on its adventure below Q1 minus 1.5 times the IQR. Data points outside these whiskers are tagged as outliers. But hold your horses, my friend. Before we label these data points as outliers, we have to exercise caution. While Tuckey's rule of thumb deems anything outside the whiskers as outliers, we ought to scrutinize the context and consider if they truly warrant special attention. Sometimes a closer look at the outliers reveals fascinating insights, while other times they might just be noise, so it's worth taking that into consideration. Let's delve into the data for the top 4 teams and see how much information the box plot preserves. When we examine the box plots, a captivating story unfolds. Man United, Man City and Newcastle, both strikingly similar plots. suggesting a consistent defensive performance throughout the season. However, there are a few matches where Man United conceded an abnormally high number of goals, which are flagged as potential outliers. These outliers stand in stark contrast to the expected performance of Man United. Now let's turn our attention to Arsenal, the Gooners. Their box plot tells us a different tale. The interquartile range for Arsenal is noticeably wider than that of the other teams, indicating a greater spread in the goals conceded. It seems Arsenal's defensive performance fluctuates more significantly throughout the season compared to their counterparts. The box plot paints a vivid picture of the variation within Arsenal's defensive prowess. Whilst the box plot provides valuable insights, we must acknowledge its limitations. In cases where the data exhibits multiple modes from distinctive groups, the box plot falls short of capturing the complete story. For example, if we came across a dataset on the age of students in primary, secondary, and sixth form, and for some reason we had some data issues and only had data for students in year 3 and year 11 due to some clerical error. Year 11 students have an average age of 16, and year 3 students have an average age of around 7. So a lot of students in this dataset are clustered around the averages for each group. When we use a box plot, it fails to compute that characteristic.
The box plot also assumes that these datasets come from the same group.
And this is where the histogram comes to the rescue. Think of the histogram as a fancy bar chart. Each bar represents a frequency count of several bin ranges. But here's the thing. Choosing the right bin range ain't no walk in the park. It's a decision that requires some thoughtful pondering. So let's dive into the art of bin range selection. It's as simple as dividing the range of our data by the number of bins we want. Picture this. If our data stretches from 0 to 100, and we fancy dividing it into 5 bins, each bin's width would be 20 units. We'd end up with intervals like 0 to 20, 20 to 40, 40 to 60, 60 to 80, and 80 to 100. Neat, right? The width of the bins can make or break your histogram. If the bins are too wide, we'll end up with bars that squash all the juicy details together. On the flip side, if the bins are too narrow, we'll have gaping holes and disjointed blocks, and our story will be harder to decipher. It's a delicate balance we must strike. Now let's talk solutions. There are various methods to tackle this dilemma. Many proposed rules use the number of samples in your dataset to determine the bin width. Directly using the number of samples will always leave us with a lot of gaps in our histogram because the width would be too small, as some blocks would more likely represent a single observation or no observations at all. To avoid that, some smart folks use the square root or cube root of the sample size to set the bin width. Your famous Microsoft Excel uses the range of your data divided by the square of the sample. And hey, some methods ditch convention and opt for using a multiple of the standard deviation to determine the range of the data, and some use more robust measures like the interquartile range to reduce the impact of outliers. Visualization tools come with fancy algorithms to choose bin widths by default. But hey, if you're feeling adventurous, why not play around with the number of bins yourself? Now let's shift our focus to the data at hand and zoom in on Man United. Turns out they have more matches where they either keep a clean sheet or concede a goal compared to the other teams. And it's more clear that the matches where they conceded 6 and 7 goals does not actually reflect how good they were defensively. One issue with histograms, especially with a smaller dataset, is that you can often have bins that are underrepresented, right next to highly represented data sources. This is because we sometimes lose information by creating these arbitrary bin intervals. Now let's explore another visualization tool that can offer us a smoother representation of the shape of our data, called kernel density estimates. Picture this. A number line showcasing the range of goals conceded in a match. If you look at one specific data point, say the 7 goals conceded by Man United, and wonder how likely it is that the team would have instead conceded 6 goals, you'd probably say there's around, an 80% chance that the team would have ended up conceding 6 goals. It's not too different. So the problem here is, how can we represent the likelihood of other matches being similar to the match with 7 goals? To represent this similarity across different types of matches, we can employ a kernel function. Think of it as a way to gauge the resemblance between various match scenarios and a particular match scenario. There are different types of kernel functions available, such as Gaussian and the triangle function. For now, let's stick to the Gaussian kernel because it's the most common one. To calculate the kernel, we need three inputs. The observation data point, in this case the match where Man United conceded 7 goals. The value of h, which determines our tolerance for considering data points as similar, often taken as the standard deviation. So if I choose a value of 2 and our dataset is symmetrical, what I'm saying is that 66% of matches that are similar to the 7-goal Manchester United match would be between 5 to 9 goals. As with the histogram, packages have some rules or algorithms that try to optimize the parameters. However, always examine your plots. The final thing is the space of data points we want to compare to our observation. So we are comparing all the number of goals that can be conceded, for example 0 to 20 goals, and we represent this as xj. Essentially, the kernel function outputs numbers we can call similarity scores to compare each data to our observation data point. We can compute a density function for that Man United match with 7 goals conceded for each number of goals in xj. Now, if we wanted to do the same for a match where he conceded 10 goals, we follow the same process. And here comes the magic. By combining the individual kernel functions at each point, we get a composite density value for the entire dataset. And how do we achieve this? Well, it's as simple as looking at all the densities calculated for each point in the data space and then summing them up. After we sum them up, we want to ensure that the area under the curve is equal to 1. So we divide the new densities of each point by the number of observed data points. Just a side note, choosing the right h value is crucial. Think of it as a knob that controls the smoothness of the density function. We started the example by choosing a h value of 1, and because of this we got a sharper density plot with more spikes. It's like capturing every tiny detail of the data, no matter how small. On the other hand, if we increase h, the plot becomes smoother, but we also start losing valuable information about our data. It strikes a balance between smoothness and capturing the essence of the data. A combination of the box plot, histogram, and kernel plot reveals a wealth of information about the data at a single glance. The peaks, spreads, and the outliers can easily be discovered. It's like having a visual tour guide to unravel the behavior of our data. In our previous discussion, we took a deep dive into the fascinating world of understanding variables in isolation. Let's not stop there. Sometimes understanding a single variable just isn't enough. Just as every note in a symphony has its place, every variable has a role to play. But sometimes we want to understand how several notes work well together, or do not work well in a musical piece. Remember, graphs help us visualize information in the blink of an eye. One of the best graphs for visualizing relationships between two variables is the scatter plot. Here's how it works. The x-axis represents the independent variable, whilst the y-axis represents the dependent variable. By looking at the scatter plot, we can see if there's any kind of relationship between the two variables. We can visually observe how variables relate to each other with a scatter plot. Is there a relationship between these variables? Is there a causal link, or do they operate independently? While we won't delve into causal verification today, we'll explore some basic methods for identifying relationships between variables. So let's go back to football and look at the metric called the goal difference. A team's goal difference is the difference between the number of goals they've scored and the number of goals they've conceded in a match. The bigger the goal difference, the higher the chances of winning. A win is worth 3 points, a draw is a point, and a loss is no points. So the more wins, the more points earned. And we all know that winning more games means earning more points. So it's safe to assume that a team's goal difference can give us a good idea of their overall performance and where they might end up in the league standings. If we plot the relationship between the goal difference and the points acquired in the last 10 seasons of the English Premier League, we see a positive relationship. Teams who have a higher goal difference tend to rack up more points. But how do we put a number on this relationship? Well, we can use something called a covariance. And it's like a measure of how much two variables change together, how they co-vary together. Here's the breakdown. We start by subtracting each variable's values from its mean. This centers the data around the mean, making values below the mean negative and values above the mean positive. We then multiply these two values together. If the two variables have the same signs, the covariance is positive. If they have different signs, the covariance is negative, meaning that as one variable increases relative to its mean, the other decreases relative to its mean. But hey, let's not get too caught up in the math. The best way to understand this is by going back to our scatter plot. Let's plot the average goal difference in total points from the Premier League campaigns we're observing. We draw a vertical line to indicate the average goal difference and a horizontal line, the average points. Now we can start visualizing the relationship. For each point, we draw a rectangle between each point and their means. In the quadrants of the plot, we seek the colors of truth, red for negativity and green for positivity. Rectangles in the negative quadrants show that x is greater than the mean of x, but y is less than the mean of y. Or x is less than the mean of x, but y is greater than the mean of y. On the other hand, rectangles in the positive quadrant show that x and y are both greater than their means, or both less than their means. If most of the points and their corresponding rectangles fall in the negative quadrant, it means there's a negative relationship. On the other hand, if the rectangles are mostly in the top right, bottom left quadrants, we're looking at a positive relationship. By summing up the area of all the green rectangles and subtracting the area of all the red rectangles, we can determine which color dominates. If there are more green rectangles than red, it's a positive relationship. And if the reds outnumber greens, it's a negative one. The covariance is simply the sum of the areas of the green rectangle minus all the areas of all the red rectangles, divided by the number of data points. So in our case, clearly there are more green rectangles, and therefore the covariance between goal difference and points earned is 487, indicating a positive relationship. But wait, there's a catch. Covariance alone isn't the ultimate solution. Imagine if we calculated the covariance for two variables x1 and y1, and it gave us 750. And then we create a new set of data by just multiplying the x value by 10 and also the y values by 10. These values would have a covariance of 75,000. Now, if we look back, x2 and y2 have just been multiplied by 10, so they should retain the same linear relationship, right? And without prior information on how the x2 and y2 were generated, our naive minds may rush to assume that the relationship between x2 and y2 is stronger because of the higher covariance, which is wrong. And this means that the scale of the covariance can increase even if the relationship isn't stronger, especially if the variables have a larger spread. And that's where standardization comes to the rescue. Let's replace y with the variable x in the equation of the covariance. Does this look familiar? Yes, because that's the variance. And if we divide this by the variance, we get 1. 1 indicates that this variable has a perfect linear relationship, since we are comparing x to itself. And this means that the maximum absolute bound of the covariance of x and y is simply determined by the product of their standard deviations. Now that we know this, we can generalize this formula by replacing back y for the x we substituted. By dividing the mean variable by its standard deviation, we get a standardized variable with a standard deviation of 1. We call it Z transformation or autoscaling for the cool kids. This is because when you rescale the variable, you're not changing the shape of the variable. You are just ensuring that the variables are measured in terms of multiples of your standard deviation. It makes variables comparable by measuring them in the multiples of their standard deviation because they're of the same unit. Since the maximum absolute bound of the covariance is determined by the product of their standard deviations, and the standardized variables have a standard deviation of 1, this beauty of a metric is bounded between -1 and 1. This formula gives us the correlation coefficient. Whilst -1 represents a perfect negative linear relationship and 1 a positive linear relationship, the story is less straightforward in the intermediate range. What about values like 0.8, 0.5, 0.2? Do they signify a strong linear relationship too? Now let's do a little exercise where I show you a few plots and you try to intuitively guess what their correlation is. Is it 0.4, 0.2, 0.3? And then I will reveal the answer for each plot I show you. It becomes apparent that coefficients around 0.5 have a closer visual affinity to 0 than 1, suggesting that a correlation of 0.5 has little to no linear relationship. But wait, as we dig deeper into our simulations, a clear pattern emerges. A correlation coefficient surpassing the 0.7 mark is a reliable indicator of a robust linear relationship. So consider anything above 0.7 as a sign of a strong positive linear bond, and anything less than 0.7 as a strong negative linear bond. But you gotta keep one thing in mind. Correlation coefficients come from comparing two random variables. Sometimes higher values can show up just by pure chance. To prove this, we ran some simulations where we compute the correlation between two randomly drawn variables with observations ranging from 15 to 100. As the sample size expands, the likelihood of stumbling upon spurious correlations steadily decreases. So be wary when dealing with small datasets. A mere 15 observations in our dataset yields a standard deviation of 0.26, translating to a 5% chance of encountering correlations between 0.52 or below 0.52 due to random chance alone. And that's saying there's a 1 in 20 chance of computing a correlation above 0.5. Can be slightly scary when you realize the amount of variables in the world. It's very important that when analyzing data with a very small sample size, you are aware that you could observe a decent correlation just by chance. And hey, who said small sizes are rare? They're all around, especially in time series data. Someone could show the correlation between two variables based on 15 years worth of annualized data. And it's easier to say that's a lot of years worth of data. But from our simulations, it's clearly not. Oh, and let me break it to you. Correlation coefficients are cool for linear stuff, but they can't handle those fancy nonlinear relationships. Like, there's this data with a correlation of 0.1. But hey, it's got a convex relationship going on between x and y. And this shows you that you have to plot your data. Your eyes are your best mates for spotting hidden gems. If we go back to our example of understanding the relationship between the goal difference and the number of points a team gets, we find that the correlation between these two variables is 0.97. This indicates that these two variables have a very strong positive relationship. Exploring relationships between variables unveils a captivating web of connections within our datasets. Through scatter plots and covariance analysis, we can decipher the relationship between variables. And when we use the correlation coefficients, thanks to standardization, we get a neatly bounded metric for quantifying linear relationships. But always remember to supplement your analysis with visual representations. Combining numbers and visualizations, that's the real deal for getting the full picture of what's going on in your data. Step into the world of data exploration and uncover hidden insights. Seek objectives that clarify complex systems, test your intuitions against the evidence, and let the combination of data and intuition shape your understanding. It's kind of through this process that we unlock the true value of the data we have. Remember, numbers alone can't tell the whole story. Visual representations breathe life into the data, allowing you to see the patterns, outliers, and nuances that numbers often miss.